Hey guys, welcome back to my channel. In this video, I'm going to be starting off a new series where I'm going over paper 1 questions in IB chemistry. This includes chemistry HL as well as SL topics. And what I'm going to be doing is I'm going to be explaining my thought process in selecting a multiple choice option, and at the end I'll reveal to you any questions I got wrong, and I'll provide you with the correct answer. So I'll try and explain the logic behind the questions I get right as well. Most of the time, I get about one wrong out of maybe 20 questions. But other than that, let's get started. So the first question says, which compound's molecular formula is the same as its empirical formula? Well, we need to remember what an empirical formula is. It shows the smallest common ratio between atoms, and a molecular formula shows the actual ratio between atoms. So if we look here, we can see that option C and D, they're both divisible by a common number. So in the first case, it's divisible by 6, and we can have one C and one H. So this is C and D are going to be eliminated. They cannot be it. And also option number D, option letter D, we can divide both by 2. So these aren't the empirical formulas. These ones aren't empirical formulas. So option C and D, we're going to cross those out. Now this one here, B and C, you gotta first use this molecular formula to construct a formula where you see just the atoms and their numbers. So I'm gonna write C, there are two C's, so 2C, H4O2. Common factor of 2, so this is not the answer. We know that A is gonna be the answer, but let's just check. So we have C2, H6, and O. Looks like we cannot divide this by another common factor, so this is going to be the empirical formula. And since we're given the molecular formula, we know that this is going to be a compound where the molecular formula is the same as the empirical. So that's going to be option 1. Option A for this question. The equation for the complete combustion of propene is shown below. Okay, remember, complete combustion results in CO2 and H2O, whereas incomplete combustion leads to CO. It literally says in the question. Which mixture, when ignited, will lead to incomplete combustion and formation of CO2? Okay, so incomplete combustion occurs when there's insufficient oxygen in order to form CO2. Notice how carbon monoxide has only one oxygen and carbon dioxide has two. So CO is formed when there's insufficient oxygen. So here we can see that for every 2 moles of propene, we need 9 moles of oxygen gas. So we need 4.5 times as much. So if we look at option A, we have 2 cubic decimeters of propene. Then the equivalent amount of oxygen we need is going to be 2 times 4.5, which is going to be 9. And we have more than that, so this won't lead to incomplete combustion because oxygen is in excess. So option A is eliminated. 0.5 cubic decimeters of propene and 2.3 cubic decimeters of oxygen. 0.5 times 4.5 gives us 2.25. Again, that's smaller than this, so we have excess oxygen. This is not the answer. 1 cubic decimeter times uh, and for DM3 of oxygen, 1 times 4.5 is 4.5. And if we have 4.5, if we have 4.5, we're not gonna have we're not gonna have enough oxygen, so this will lead to the incomplete combustion because we need 4.5 moles of oxygen, or volume of cubic decimeters of oxygen, to completely combust 1 dm3 of propene, and we don't have enough, so this will lead to incomplete. And 3 cubic decimeters of propene, 3 times 4.5 is 12 plus 1.5, so 13.5. We have excess oxygen, this is not it, so C is the correct answer. What is the percentage yield when 1.1 grams of ethanol is obtained from 4.6 grams of ethanol? Okay, we're getting ethanol from ethanol, so we're going to be considering this equation right here. So we have an oxygen. I think this is meant to represent an oxidizing agent, not an oxygen, so that's something to keep in mind. This does not mean concentration in this context. And percentage yield, so we've made 1.61 grams of this, 1.1 grams of ethanol. Okay, that's our product. And we know that in terms of ethanol, we have the molar mass is this, 44. So we've made 1.1 divided by 44 moles of this. Right? Where to calculate moles, we're doing mass over molar mass. That's why. Next up, we need to divide this by, since this is the product, we need to divide this by the theoretical yield we had. So when we had 4.6 moles of ethanol, we were meant to make 4.6 divided by 46. So this is the number of moles of ethanol, sorry, we reacted. So in terms of theoretical yield, we expect the theoretical yield to be based on how much reactants we use. So here we use 4.6 divided by 46, so 0.1 moles, but we're not going to write that there because the answer options don't have that. We've had this many moles of ethanol, so we expect this many moles of ethanol. So the final answer is going to be, if we find the reciprocal, 46, 44 times 4.6 times 100, remember, because it's a percentage. So it looks like option, this is eliminated, this is eliminated, this is eliminated, option A is correct. Okay, this question's a bit weird, I think. Which stage of operation immediately follows ionization in the mass spectrometer? In mass spectrometer, we have ions formed of a molecular compound, and they're generally positive ions, and then the neutral atoms remain. So I think mass spectrometers, they don't deflect particles. Deflecting particles is something else. Wait, no, it is deflection, right? Maybe it's deflection, but detection, no. Vaporization, no. These don't make sense. It's either deflection or acceleration, and I think it might be deflection. I might go with deflection, but also I'm sort of starting to remember that mass spectrometers do accelerate the ion, so I might go with A for this question, but we'll see at the end whether it's correct. Which statement is correct about the first ionization energies of consecutive elements shown in the graph? So first ionization energy is the energy required to remove 1 mole of gaseous electrons from 1 mole of gaseous atoms in their standard state. So when we look at a first ionization energy chart, we need to see where there are drops. So from here to here, there's a drop. Here to here, there's a drop, and big rises. Okay, so these provide insights into what type of electron configuration an atom would have. When there's a drop, that means there's a reduction into electron repulsion. So you have like doubly occupied orbitals becoming singly occupied. So if we remove this one, it actually lowers the thing. It increases, so it lowers into electron repulsion, increasing ionization energy. So we look at that stuff. The graph falls between beryllium and wait. So this says okay. The graph falls between beryllium and boron because there's an electron configuration. There's an electron in the third energy level. Okay, third energy level electron. Oh, okay. So I forgot to read the bottom bit, which says atomic number. So we're looking at hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluoride, neon. Okay, that's cool. So the graph falls between beryllium and boron, hydrogen, helium, lithium, beryllium to boron. It falls because there's an electron in the third energy level. Well, uh, actually, it's because that could make sense because when you go from beryllium to boron, we're occupying a 2p orbital, which is higher energy than the 2s orbital of beryllium. So higher energy electrons are easier to remove, hence requiring less ionization energy. So this could be an option. The graph increases from boron to nitrogen because the atomic radius is increasing. That does not make sense. If atomic radius increases, electrons are further away from the nucleus. Electron to nucleus attraction is lowered, so it would be a lower ionization energy wouldn't be increasing. This option's eliminated. The graph increases from lithium to neon because the number of electrons is increasing. That does not make sense because there are literal falls between these. The graph falls between beryllium and boron because the outer electron in boron is in a p subshell. Oh yeah, oops, this one's wrong because it says third energy level. It's actually still in the second energy level. My bad. It's in the 2p. I didn't see that part. I should have paid more attention. The graph falls between beryllium and boron because the outer electron is in a p sublevel. P sublevels are further out than s sublevels, so they're going to be experiencing less electron to nucleus um, attraction or force keeping it together, so less energy is required to remove the electrons, so lower ionization energy. We're going to go with option D. which element has the greatest first ionization energy? So we're going to look at something that has electrons that are really hard to remove. So we have argon, aluminium, and cesium. So already, I'm not going to pick cesium or aluminium because we have argon and chlorine, which are a noble gas and halogen respectively, and that means that we're not gonna. That means that we're not gonna have. Uh, we're gonna have these molecules which like having more electrons, and removing electrons with something that likes electrons will require a lot of energy. So argon is a noble gas, chlorine is a halogen. I'm going to go with argon because it already has a full octet, so meaning it's unlikely to lose any more electrons because it's unfavorable. Which elements are the same group? Which elements are the same group of the periodic table? Okay, so cadmium, rubidium, strontium. So this one seems to work. You can use the periodic table. So I'm not going to scroll up to it, but or open one. I'm just gonna go to the periodic table. This is just looking at the periodic table, seeing which one's in the same column, and I'll tell you guys the answer. Okay, so from the looks of it, A is not an option because uh, cadmium is not in the same as sodium. Argon is not the same as aluminium, silver, platinum. That could be right. Phosphorus, bismuth. I need to check those. After checking, I realized that lead and platinum are not together, so it must be D, which is in the same group. Which property of transition metals enable them to behave as catalysts? Transition metals partially filled D sublevel, so high melting point, no. Split D sublevels. Um, that's more to do with light energy. Because, light ligands and absorbing light. High density, no. Variable oxidation number is probably the right one. Okay. Which statement best describes the lattice structure of solid sodium chloride? So sodium chloride in a lattice structure would have sodium surrounded by chlorine on all six sides, and each chlorine surrounded by sodium on all six sides. Chlorine ion, nope, nope, nope. It's six. It's going to be D. Which compound is most likely to contain ionic bonding? So ionic bonding would be between a nonmetal and a metal, generally. So this was eliminated to nonmetals. Cesium, chlorine, that could work. I think. I'm not sure. Alpha chlorine, no, no. Silicon is in the same group as carbon, so I'm gonna pick. Not gonna pick this. I'm gonna go with B for this. Which molecule is polar? Polar means charge separation existing, so this one is gonna have symmetry. So that's not gonna be a polar option. This molecule is gonna be asymmetrical, so I'm gonna say this molecule does have polarity. It depends actually. So let's just check the other options. This one definitely doesn't. This one doesn't. So B definitely does. So I think the structure might look something like this. Like something like that. The structure doesn't really matter. You can eliminate the other options and get B as your correct answer. What is the shape of the hexacyanoferrate ion? Okay, so this is going to be octahedral, so trigonal bipyramidal is 5. So we're looking at electron pair geometry. Now I'm wondering though, is this going to be square planar in octahedral or octahedral? I know hexagonal is not the case. Um, so the ion here is going to be iron 3 plus because this whole charge is going to be -3, and each cyanide contributes -1, so -6. And since we have -3 as our final charge for our complex iron must be 3 plus, or +3, sorry. It should be +3. So if iron's +3, based on its electron configuration, it should have some non-bonding electrons. But my question here is, when they say the shape, do they mean the molecular geometry or the electron domain? Now, given that I have two options, the hexagonal is eliminated, that's not a real thing, but we have octahedral and trigonal bipyramidal. So I think because these are both electron geometries, and this is a molecular geometry, I think I'm going to go with octahedral because square planar is a molecular geometry, and that's the only option that's a molecular geometry. I think it's trying to throw us off. And in terms of a complex ion, I don't think you really consider the non-bonding electron pairs. So I'm going to go with C for this one. Which set contains two or more species with delocalized pi electrons? Delocalized electrons are free to move between atoms in a bond. So if we look at it here, this should be generally a resonance structure. So this is eliminated, this is eliminated. So this option cannot be it, this cannot be it, this cannot be it. Actually, no, benzene, that does work. And this one molecule that doesn't work. Carbonate ion, that does work. This one works, this one doesn't work. But since we have two or more, C seems to be the right option. This doesn't work, this doesn't work, this doesn't work. So C is our correct option. Which of the following changes are exothermic? Exothermic delta H is negative, and negative delta H. Let me just write negative delta H. That means energy is released from the system into the surrounding. So generally, we have an acid and a base mixed together. A neutralization reaction, um, which is in fact an exothermic reaction. We have a combustion reaction, combustion burning of fuels. We do that in our cars. We get a lot of energy released, and we have gas becoming a liquid. Ooh, that means that there are going to be more energy. There's going to be more energy stored in the intermolecular forces between the molecules, so that'll be taking in energy. So it's just going to be this and this, not this. And so it's going to be one and two. A. Wait, no, no, no. Actually, I just remember making bonds. Wait, is it making bonds is exothermic? Making bonds is exothermic. It's always the counterintuitive option. You think breaking bonds is uh, exothermic, but no. Making bonds is exothermic? Yeah. So if we're making bonds, it's exothermic. Let me just think of it the other way. So if we go from a liquid to a gas, we put in energy, right? Because we need to vaporize it. Yeah, we need to vaporize a gas, a liquid to make it a gas, and that is endothermic. So the opposite must be exothermic. So I think maybe it might be all three. I'm not sure. It's just I get a bit confused when it comes to this energy stuff. In terms of making and breaking bonds, I think I just got to revise topic 5 a bit. But maybe it's D or A. I'm not sure. Look at it at the end. I just think that maybe because liquid to gas is endothermic, the opposite should be exothermic. That would make sense. But let's just move on to the next question. Which change represents standard enthalpy change of formation? Formation of one mole compound from a standard state from its gaseous atoms. That sort of works. One mole compound is for its elements. Okay, one mole compound from a standard state from its gaseous atoms in their standard state. This one seems to be the most comprehensive. Formation of one mole compound in a standard state from the elements in their standard state. Okay. I think gaseous might not be a component. I remember standard states being a major component of this standard enthalpy change of formation definition. So I'm gonna go with D for this one. It's gaseous, doesn't work. And one mole of compound is standard state from its elements. I think standard state's important as well there, so I'm gonna go with D. Which equation represents electron affinity? Electron affinity is in a gaseous molecule, so this one's wrong. This one could be right, and if we gain an electron, this cannot be. So this is being further ionized, so no. Half, half Cl gas. Okay. Um, this one seems to work. This one also seems to work. Electron affinity energy. 1 mole of electrons is added to 1 mole of gaseous atoms. Okay, so it's either carbon or chlorine. Now, chlorine works. I know that chlorine does have electron affinity, but I'm wondering if it is 1 mole of gaseous atoms because I understand that the molecule contains 2 moles and it's one half, so it's 1 mole of chlorine atoms in total, but I'm just unsure which one to pick. So they're both correct in terms of becoming negative. But I think that given we have a gaseous, I mean, a molecular chlorine here with two, I don't think that's correct. I think I'm gonna go with A for this one, because in the electron affinity definition, I think you need a mole of a substance or mole of an element to gain electrons. Which combination results in an ionic compound having the greatest magnitude of lattice enthalpy? So magnitude of lattice enthalpy would increase when the ionic bonding is stronger. Some of the ionic radii should be smaller because ionic radii smaller means that the electrons or the molecule itself is more tightly packed. The charge is more packed, So the stronger charges would mean that the stronger attraction. Ionic charges are larger. Larger. So these options are eliminated, the small ones. So it's going to be A as our final answer. Under which conditions does a sample of the same mass of carbon dioxide have the lowest entropy value? Okay. Entropy value. Entropy is a measure of the disorder, I think, and the same mass of carbon have. Oh yeah, so high entropy means high disorder, low entropy means low disorder. So lowest entropy would mean when they have a solid. So solids are more ordered than gases, so they have lower entropy. And low temperature means less movement, so less disorder. So we're gonna go with B for this one. Curves 1 and 2 represent samples of the same gas at a constant pressure but at different temperatures. The areas under curves 1 and 2 are equal. What does curve 2 represent? Curve 2 is a lower temperature. Nope, this is a higher temperature because we have a greater proportion of particles in a higher kinetic energy. Curve 2 is at a lower temperature. Nope, again. Curve 2 is a higher temperature and there are more molecules in the sample. Not necessarily. Because the area is the same, that means the molecules are the same. Number of molecules is the same. Curve 2 is at high temperature, there are the same number of molecules. That's correct, so it's option D for this question. The graph shows a plot for a reaction with second order kinetics. Second order means that we have something to the power of 2, with the reaction order being 2. So y-axis, x-axis, and looks like we have something increasing greater than proportionally or an exponential rate. So the x-axis, we're going to have concentration because based on this, I don't think over time reaction rate would not increase. So the y-axis is generally concentration or reaction rate, but either one won't really increase over time. So it has to be the y-axis must be rate. So y-axis has to be rate, and D must be the answer because the x-axis itself it cannot be something that so the y-axis the dependent variable cannot be the dependent variable cannot be time because you don't put that in the y-axis. Time you kind of like time's not dependent on stuff. It cannot be concentration because over time concentration cannot increase. It should decrease as the reaction progresses. So it must be rate. So I can already pick option D for this. Which factor affects the rate constant of a reaction? Rate constant is how fast something's going. This does. Concentration of reactants, remember, that actually affects the square bracket, so it does not affect this. And temperature does affect it because the rate constant is temperature dependent, so it's going to be 1 and 3. Which best describes a reaction in a state of equilibrium? Rates of forward and reverse reactions are zero. Nope, the reactions haven't stopped. That's one of the factors in equilibrium. The reactions are still going. Rate of forward reaction equals the rate of reverse reaction. The concentration of products and reactants are equal. That's not true. The concentrations are not always equal because sometimes equilibrium can be shifted to the right or more towards the right. Sorry. So that could lead to like a strong acid would have an equilibrium that's more towards the products than a weak acid. The rates of forward and reverse reactions are zero. Again, wrong. So it must be D. Rates of the forward reaction equals the rate of reverse reaction, and the concentrations of products and reactants are constant because the concentration of reactants and products is determined by the rates of the forward and reverse reaction. If they're the same, these two are going to remain constant. The equilibrium concentration of X, Y, Z, and W are 1, 2, 4, and 2 moles respectively. Okay, what is the value of the equilibrium constant? Okay, so we got K, and Kc is equilibrium constant, and we're going to do Z to the power of 1, W to the power of 1, over X to the power of 1, and Y to the power of 2. So if you guys don't understand this, please refer to a, a a video on how to calculate the equilibrium constant. I'll probably make one. If you guys want me to make one, please write a comment down below if you think that would be helpful and worth my time. Alright, so Z would be 4 moles, W would be 2 moles, and X would be 1 mole, and Y would be 2 moles squared. So 2 squared is 4, 4's cancel out, and we get 2 as our final reaction order because 2 over 1. Sorry, not reaction order, equilibrium constant Kc. Which of the following molecules can act as Lewis acid but not Bronson-Lowry acid? Lewis acid is able to accept an electron pair, electron lone pair, electron pair. Bronson-Lowry acid donate proton. So let's see. BF3 boron is something an exception to the octet rule, so it's fine with having 6. It's going to be looking like this. So F, F, and it's going to have 6 electrons, so it's an octet rule. It's an exception to the octet rule, so this one's fine. A is not the option. P, potassium chloride. I remember this one. I remember this. This has a trigonal bipyramidal structure, I believe, and so it's going to have excess electrons in its shell. So it's not going to be the answer because it's going to be acting as a Lewis base. A Lewis base. Ammonia is going to be an acid and base, anyways. We all know that ammonia is a base. Water can act as a Lewis acid, and as a Bronsted-Lowry base, it does not really doesn't really does water really act as a Bronsted-Lowry base? Um, I don't think so. So I must have done something wrong because this one does actually act as a Bronsted-Lowry base as well because it can protonate itself. So let's go over the answer options again. So we said that um, BF3, it's an exception to the octet rule. It's fine with having 6 electrons, but just because it's fine, I think it can still gain electrons. So I like all these options I know are definitely wrong, but this was the only weird one. So I'm gonna go with this one because I know that these options are definitely wrong. I eliminated this one at first because I thought that since it's an exception to the octet rule, it cannot act as a Lewis acid and accept more electrons. But given that it does have an incomplete octet, and even though it's fine with it, it does still want a full octet. Then I think that boron uh, might be the correct answer here, which is a 0.001 molar solution of weak acid. Conductivity, again, has to be poor because it's a weak acid. It's partial dissociation. pH would not be 10 because that's towards the base. It would be more towards this. A bit lower than pH 7, which is neutral, so A is the answer. What is the order of increasing acid strength? Approximate Ka and pKa values. Okay, so we're given the Ka, pKa values of these substances, and the higher the pKa value, the weaker the acid, and the higher the Ka value, the stronger the acid. So this one is going to be, well, let's convert this to one standard measure. So if we find the pKa of this, it's going to be 3. If we find the pKa of this, it's going to be 5. So again, lower the pKa, the stronger. So this is going to be the strongest. Again, this is a carboxylic acid, so it's going to be really strong. And this one's also got a chlorine, so it's going to be go from 3 to this one. So it's going to, looks like it's not going to be this option. It could be one of these. It's not going to be this option. It's going to be not going to be this option. It's going to be this option because we have strongest, second strongest. We know these two are the strongest and second strongest. And so this is the only one that follows the rule, so it's going to be D. Okay, next one. Which solutions mixed in equal concentrations and volumes form an acid buffer? So an acid buffer means we can resist change and it's going to be sort of acidic. So to create an acid buffer, you need a weak acid plus salt of strong conjugate. So we eliminate hydrochloric acid because it's strong. Ethanoic acid, I believe, is definitely correct. I think, yeah, it's definitely correct. I've heard of this buffer. So I think it's going to be 27, or sorry, it's going to be B, I think, for this one. Next option, which salt forms the most acidic solution when dissolved in water? So most acidic means we're going to look at the strongest acid, so sodium chloride. No, it's not going to be it. Magnesium chloride, nope. Nope. I think it might be, actually, I'm not sure entirely. Um, Most acidic solution. I'm not really sure how to do this one. Honestly, I'm ionic radius. Maybe it's the smallest ionic radius. I might pick A because it's the smallest ionic radius. Yeah, because NaCl, I know that doesn't have that much dissociation, so it's not going to be that. And yeah, I'm just going to go with smallest ionic radius because I don't see any other reason why this is given as an option. This is a bit of a guess though. Okay, what is the buffer region for the acid-base titration? So the buffer region is a region for which there's a resistant pH change. So uh, I think it might be A. So with C, right? Wait, why can't I? These both look like buffer regions, but volume of alkali added. I think maybe A is the better buffer region because when you have the buffer being added, there's a bit more of a steeper change here. That's more noticeable, so that's kind of bad for a buffer. But whereas this one's really flat, so I'm going to go with A. Which element undergoes reduction in the following reaction? Okay, I believe that for this one is 4 plus and neutral overall, or minus 1 overall, so this is going to be minus 3. That's going to be minus 3 and it becomes 0, so that's not going to be reduction. But I believe it is chromium because I've heard of chromium going over reduction. In dichromate, so this is the dichromate, no, something else, some other chromate ion, but this is a minus 2 charge, I know that for certain because this is plus 2, this whole thing is plus 2. Since this is 2 minus, we have minus 14 to become 2 minus x would have to be 6. And then this compound we have 6 and so minus 6 plus 2x equals 0, x equals positive 3. So we see that charge itself is reduced. So this is going to be reduction, chromium C answer. Which best describes reduction, increase in oxidation number, and gain of electrons. Gain of electrons is right. In reduction, oxidation number decreases, so we eliminate these two. Gain of electrons is correct, so C is on. What is the value for E in volts for the following reaction? VO2 plus, V2 plus. Okay, so vanadium, I think, said electron potential. Okay, so this question, it looks like we're having. It's actually quite difficult. VO2 plus. I think first I need to identify which of these reactions is actually happening. So vanadium dioxide is not the reaction that's happening. Vanadium 2 plus is reacting to form vanadium. So vanadium 2 plus is forming vanadium 3 plus. So it can't be this equation because we don't have 2 there. So it's going to have to be this equation but reversed. So it's going to be 0.26. So we're having this one losing, this one gaining electrons, or losing electrons, right? Vanadium 2 plus losing electrons. So this is going to be a reduction value here. So losing electrons is oxidation. So we're going to switch the value to make a reduction value. Sorry, oxidation value of 0.26. For this one seems to be in the right orientation or right order here. So and the mole ratio seem to be fine. So I'm going to go with plus 0.304. So if we subtract the if we go for 0.34 minus the oxidation, so let me just write out the formula. I think it's E potential, right? Yeah. They'll tell you standard conditions is standard enthalpy, standard energy, or standard electron potential. Sorry, my words are getting a bit messy. Standard electrode potential of the reduction reaction minus standard electrode potential of the oxidation reaction. So it's going to be 0.34. Take away 0.26. I'm going to go with 0.008 for this one. What product is formed at the positive electrode when, okay, so positive electrode is the anode oxidation, so the sulfate ion. So it's really low concentration, so I don't think the sulfate ion is going to be affected. Plus, I know from order of discharge that sulfate is the weakest one, so it goes OH minus is more likely than Cl minus, which is more likely than SO4 2 minus. So I'm going to eliminate these two options. So it's going to be oxygen, hydrogens at the cathode. So it's definitely going to be B. Which pair of compounds can be distinguished by reacting them with dilute bromine water in the dark? So dilute bromine water in the dark is referring to alkanes and alkenes because alkenes do react with bromine water because they contain the more polar double bond, and this double bond being more polar means that we can have more it can actually readily react with bromine in bromine water and it can form a dibromide compound. And so we got this and this. Which one do I pick? Well, first of all, we've got these options. We got A for carboxylic acid, so I'm not gonna choose that. This one right here, I see there's a double bond here. Yep, there should be a double bond in this bit. And this one looks like a single bond, so this one could work because it's an alkene and alkane. This one seems to not be the case because we have two CH3 groups attached. Yeah, I don't think that's the case. That's just that just has a methyl group, I believe, um, and it's still an alkane, so there's no point in doing that one. This is also an alkane, so this option's incorrect. This is a bromo compound. We're not going to do that because if we're distinguishing by dilute bromine water, we're going to be reacting it with bromine. If it's already reacted with bromine, as in it has a bromine atom in this compound, there's not going to be a point in doing that one as our answer. So we're going to go with option B. Which compound is most soluble in water? Okay, so first of all, I know that the carboxylic acid contains. So we have two carboxylic acids, these two, and we have two alcohols. Wait, is that an alcohol or is that an aldehyde? I believe. Actually, let's see. So if we draw out the first structure, it should match the second one. We got, let's just write H3, H2, and this one has a H. Okay, so it needs to be double bonded to oxygen. So these two are both aldehydes. Aldehydes are relatively weaker than, or less polar than carboxylic acid, so it's going to be either option C or D. Now, since its solubility in water, I believe the longer a substance is, the bigger it is, the less soluble it is in water. Because remember, if for water to solvate a compound, water molecules have to surround that compound, right? Surround it completely, and cause it to dissociate. So, smaller compound is more soluble. So, since this one's small, I'm gonna pick C. Which are the features of successive members of homologous series? Similar chemical properties, yes. Physical properties are the ones that diverge. Same general formula, yes. Differ by CH2, that's correct as well. So I'm going to go 1, 2, 3 and pick D. Which formula represents propane nitrile? So the nitrile is the. Okay, so I think nitrile is a triple bond to nitrogen. So already I can see these are amines, yeah. So these won't work, or amino compounds. And one of these is a nitrile, and since this one has 1, 2, 3 carbons, I'm going to pick this one because propane is 3 carbons, whereas this one has 4 carbons, so that's going to be butane, so I'm not going to pick B. And these ones are already eliminated, so I'm going to pick A. Which halogen reacts fastest with warm sodium hydroxide? Okay. A halogen reactor with sodium hydroxide, we're thinking of um, a nucleophilic substitution reaction. I believe it's substitution, right? Nucleophilic substitution reaction of a halogen alkane. And the fastest is the SN1 mechanism because it's faster than the SN2 mechanism. And if we're looking at the SN1 mechanism, we're thinking of tertiary halogenoalkanes. So tertiary halogenoalkanes. Alkanes. So already we can see these are primary. Primary, we can eliminate them because they follow the SN2 mechanism, which is two-step. It's slower than the SN1 mechanism. And next we have bromine and chlorine. And remember, in the SN1 mechanism, we have a heterolytic fission reaction between the. So we have carbon, CH3, CH3, CH3. I'm just drawing out option A. Actually, no, let's do option B. Bromine. So we see here that the carbon to bromine bond is going to be there. It's going to be the one that has a most electronegative difference. So carbon is partially positive. This one's partially negative. And what happens is heterolytic fission, where the bromine takes both electrons in the bond, leaving carbon positive. We form the carbocation intermediate. And this one can bond to the OH minus in solution in the sodium hydroxide. But since we're looking at the bond breaking, since we're going to be looking at the bond breaking, we're going to think about which bond is weaker. So if we have so C to Cl compared to C to CBr, this one has a higher electronegativity difference, so this one's stronger. Since the bond is stronger, it's going to be harder to break heterolytically. So this one's going to be slower in forming that carbocation intermediate. And since that's the slow step, this one has a lower reaction rate. So it's going to be we're going to have to eliminate this option, pick B. What is the geometric isomer of cis-1,2 dichlorocyclopropane? It's a tough one. So cyclopropane, already since it's propane, there are no double bonds. We can eliminate this one. And since we have dichloro, um, we have one chloro, two chloros, and this one's eliminated. 1,2 dichloro. This one seems to be fine. Let's look at option C. This one also seems to be fine. Cyclopropane, they're all cyclo. Um, but cis means they're on the same side, and trans means they're on opposite sides. So if we look here, we have the chlorine, one on the bottom, one on the top. So that's going to be a trans molecule. So this one has to be the answer because cis means same side, which it is the case here, and option C is trans. So we're going to be left with option A. Okay, which is the best line of fit or line of best fit for the points plotted on the graph? Okay, so this one's not the line of best fit because it literally connects the dots. It doesn't really help show a trend line. This option quite similar. I'm thinking with this option it only goes through 2 points, so that might not be the answer. This one goes through 1 and 2 points, and this one goes through 3 definitely. So this one is definitely the contender for having going through the most number of points. Well, when you think about divergence, right, of the points or the residuals of the points, so we're getting a bit into math. If you're looking at how far the points are from the trend line, this one is clearly the closest. This one has the furthest point, so the second furthest. This one has the closest point. So I would go with this one as being the best line of best fit. So now it's time to go over the questions we got wrong. So this question right here, I did get wrong. So it says the buffer region. What is the buffer region in the acid-base titration curves below? So I said it was option A, but it turns out it was option C. Option C turned out to be the right answer. So let me just write that in red. I think it's to do with this buffer region being too shallow here, and the sun being just the right steepness. I think that's might be the reason. And yeah, other than that, I don't really see any other reason. If you guys do see another reason why this option C is correct, please just say in the comments acid base titration and right why C is correct, because sometimes IB mark schemes, so I use the mark scheme for this question, do get them wrong sometimes, but I'm not sure if this is one of those times or I'm wrong. It's probably me wrong, but if you guys have a better explanation, please write in the comment. And also, this question turned out to be wrong, which actually made me quite sad. It turns out this formula I used is actually incorrect because you're meant to add these two together, so I would have got 0.60. So C would have been the correct answer. So you do the minusing if you don't change this one to the oxidation one. If you don't change it to the positive version, that's when you use the minusing. So minusing a negative would give you a positive. So that's the mistake I made. And for this question, it turns out this was not the correct answer. It was C that was the correct answer. So turns out this was the cis molecule, which is kind of confusing. But there you go. That's the answer for this one. So um, even though these are on the same side, and the mark scheme does say this one is the cis molecule, which is quite confusing to be honest, because I have no idea why that's a cis molecule. So I'm sorry that I don't have an explanation for that, but if you guys do, please write in comments below, because of course I'm not perfect. I'm not sure how to answer this one. The answer could be wrong. I have a strong feeling, but then again, I could be wrong. So yeah. So in total, guys, we managed to score 37 out of 40, which is pretty good. Um, Considering we did it with like 50 minutes of the time remaining, so like 45 minutes. And other than that, guys, I hope you enjoyed this video and learned something new that helped you prepare for your chemistry exams. And like always, this is a small channel, so any help is appreciated. So like, subscribe, comment, anything you want, and on the comments below, please write any video recommendations or topics in IB subjects you want me to cover. I'll be happy to do that. And other than that, see you guys in a future video. Peace out.